Is Oscar Higott, who's going to be giving the first of a series of talks about Floquet codes.
Thanks. So yeah, I'll be talking about constructions and performance of hyperbolic and semi-hyperbolic Floquet codes. And this is joint work with Nikolas Breuckmann. And you can find the archive ID there. Okay, so the motivation is the same as for many of us here, which is that quantum error correction is very expensive. And in particular, for architectures that require operations that are geometrically local in 2D, then these two graphs on the right here illustrate that, say, at physical error rates of around 10 to the minus 3, with either full circuit level noise or with pair measurements, you might need around 1,000 physical qubits per logical qubit. And that translates into requiring millions of qubits for fault-tolerant applications. And so a potential solution we've had a lot about this week are LDPC codes. And now we know, of course, that good quantum LDPC codes do exist with finite encoding rates and linear distance. And so there's hope that we can do a lot better than the surface code. But in practice, we need to implement a quantum circuit on hardware. And that is constrained by gate and measurement noise and the available native physical operations. And the connectivity of the device, both the degree of the connectivity and the geometric locality. And also, we want to implement some finite size. So the asymptotic scaling might not be so important. So we're constrained by the physical size of the system. And this work is, in some sense, sort of extending some, or related to some previous work with Nico on hyperbolic codes, which have a finite encoding rate and logarithmic distance, and have asymptotic scaling that improves on the surface code. And so in this work, we looked at reducing the check weight of hyperbolic codes using subsystem codes. So we used weight 3 checks and found a 4.3 times saving for circuit level noise at sort of reasonable physical error rates and pseudo thresholds above 0.5%. And the flexibility that allowed these kind of efficient circuits and low check weight is that subsystem codes allow the kind of instantaneous stabilizer group to vary from measurement to measurement. But there's a question of, can we do better? Can we achieve better logical error rates, better overheads at reasonable physical error rates? And that's what we look at in this work. So this work is on hyperbolic Floquet codes. And so we construct and study families of Floquet codes derived from hyperbolic tilings. And these have weight 2 check operators, degree 3 qubit connectivity. And we show that depending on the available native physical operations and the error rates, these can result in around a 5 to 100 times saving in qubit overhead compared to surface and honeycomb codes. And I'll explain what I mean, in what context we get these improvements in this talk. Additionally, so these are just Floquet codes. They can be decoded with matching or union find, and we find they have the same, essentially the same threshold as honeycomb codes. So what are Floquet codes? They're defined on a 3-colorable lattice, where each edge is the color of the face it connects. So adjacent faces have different colors, and we assign one of 3 colors to each face. And then this blue edge here, for example, links these 2 blue faces. And so we measure weight 2 anti-commuting checks, where we have an XX on each red edge, a YY on each green edge, and ZZ on each blue edge. And the stabilizers of the Floquet code are these contractible loops of edge operators. Now, if you were to treat this as a subsystem code, if you were to treat each edge operator or each of these weight 2 gauge operators as a gauged operator of a subsystem code, then you would find that the stabilizer operators of the subsystem code are all loops, closed loops on this tiling. And that includes the homologically non-trivial loops. So for example, with these toric boundary conditions on the right here, the ZYX operator is a homologically non-trivial loop, which commutes with all the check operators and is also in the gauge group. And so if this was a subsystem code and we fixed all of these stabilizers, and it can be shown that there would be no available logical degrees of freedom. But the result of Hastings and Ha was that for some specific schedules, so for example, if you measure XX on the red edges, YY on the green, and then ZZ on the blue, and then repeat, it can be shown that this only measures these bicolored cycles, which are by definition homologically trivial. And so the homologically non-trivial cycles are preserved. And so we do have some logical degrees of freedom which are protected. Now, one useful mapping that I'll consider in this to better understand the codes in this talk is the embedded homological code. So after measuring, say, here the red edges, each edge is projected into a 1-qubit subspace after measurement. And we can think of this as forming an effective qubit and an embedded homological code. So on the right here, this dotted line, this hexagonal lattice with the dotted lines, is called the red restricted lattice after the red edge measurements. And each edge of this dotted lattice corresponds to an effective qubit. And we can think of this as defining some homological code. So for example, after measuring this red edge here, we projected this into a 1-qubit subspace, which has an effective Z operator of IX and an effective X operator of YY. And therefore, the stabilizers and logicals of this embedded homological code can be mapped to the stabilizers and logicals of the Floquet code, which can just be useful to understand the structure of the Floquet code. And so using this mapping to define a basis for the logical operators, we obtain this for the toric honeycomb code on the left here, this X0, Z0, X1, and Z1. And the inner logical operators I mentioned before, these homologically non-trivial loops which commute all the checks, are on the right here. And these are products of this X0, Z1, and Z0, X1. The logicals on the left, these are just after the red edge measurements. They commute with the subsequent green edge measurements, but they anti-commute with some of the blue edge measurements. And so we'll see that the logical operators have to evolve over time. So all Floquet codes, including the hyperbolic ones in our work, can be decoded straightforwardly with matching. And the way this works is just like for the surface code, you can pair consecutive stabilizer measurements in consecutive rounds. And here, each stabilizer is formed from the product of 6 edge measurements. And so you form a detector from the parity of 12 edge measurements spanning 5 sub-rounds. And then you can use STIM to construct a matching graph, which can then be decoded with matching or unifying. So decoding is efficient and straightforward. So in our work, we consider Floquet codes from hyperbolic tilings. And it's known that you can construct a Floquet code from any color code tiling. And a color code tiling is just a tiling with 3 colorable faces and degree 3. And so Christophe Rio proposed using hyperbolic color code tilings in the paper reference 2, and noted that the asymptotic parameter scaling is just the same as for hyperbolic surface codes. So you have a finite encoding rate and logarithmic distance. And so this leads to this sort of ratio of kd squared over n being equal to log squared n. So this is an asymptotic improvement over the surface code where this would be a constant. But previously, explicit examples had not been considered, so the performance of these codes was not known in practice. So in our work, the color code tilings we construct, we use the Wittoff's kaleidoscopic construction. So the tiling is generated through sort of reflections across the sides of a triangle. And we can generate, also, for example, on the right here, there's 4, 8, 10 tiling. This is the vertex configuration of this uniform tiling, which means that each vertex is surrounded by 3 faces with 4, 8, and 10 sides. And we can more generally generate a RGB uniform tiling from the triangle group generated by triangles with internal angle, a triangle with internal angles R over 2, G over 2, and B over 2. And then we generate finite tilings from quotients of these groups. And these are hyperbolic if 1 over R plus 1 over G plus 1 over B is less than a half. So there are infinitely many tilings we could consider, but the ones we choose are these, the 888, 4810, and 41010 tilings. We choose these just as they have small stabilizer weight. So the embedded, if we then look at what the embedded homological codes look like, say for the 888 Floquet code, I've drawn on here like the red, the green, and the blue restricted lattice, where here each restricted lattice is 4 octagons around each vertex. And we define the embedded distance of a Floquet code to be the minimum distance of any of its 3 embedded homological codes. And note that this distance is lower than the kind of the code capacity distance of the Floquet code. We're talking about the distance of the embedded homological code, which is associated with pairs of qubits. But this embedded distance is almost exactly the same as a useful circuit level distance metric and easier to compute. So the smallest example we show is this Bolster Floquet code, which is a Floquet code derived from an 888 tiling of the genus 2 Bolster surface. And so on this diagram, we see that opposite sides are identified. And this encodes 4 logical qubits into 16 physical qubits. And so as an example, here are the logical operators of the Bolster code, the 4 pairs of anti-commuting X and Z operators. And for each logical operator is defined by a homologically non-trivial loop on the tiling. And the support of the logical operator is entirely within this homologically non-trivial loop. And then the form of the operator evolves over the schedule. So the evolution of the logical operator is sort of within the support of this logical path, and the logical path is used to update the logical operator over time. So more specifically, as I mentioned before, there's no static generating set of logical operators for Floquet codes. So this is sort of the extra flexibility we've gained in some sense over subsystem codes. And the way you update is after the C subround, where C is a color like red, green, or blue, we multiply the C checks into the logical operator if they lie within the homologically non-trivial logical path. So I mentioned that the codes we consider have logarithmic distance, and that might be a concern, especially if we want to achieve, say, 10 to the minus 12 logical error rates or lower, without using exponentially large system sizes. But fortunately, this problem can be solved by weakening the curvature of the semi-hyperbolic lattices. And then we can obtain families of codes that have distance scaling as square root n, but still retain a large constant factor improvement over honeycomb codes and surface codes, even for arbitrarily large system sizes. So we can achieve an n over k is equal to c d squared for some much smaller c than toric or honeycomb or surface codes. So I'll show how this construction works. So if we start off with some hyperbolic color code tiling, I've drawn in white here the dual lattice, where we've exchanged faces and vertices. Now if we consider only that dual lattice, so we now have triangles and 8 triangles meeting at each vertex, we then fine-grain this lattice. So in each triangle, we fine-grain with a triangular lattice, like so. And then we again take the dual, which is now this blue lattice, this blue dotted lattice. And essentially, you've inserted hexagons into the tiling and weakened the curvature, and it allows you to increase the distance, achieve distance scaling as square root n, as I say. And this gives us many more codes to consider and much higher distances. So the circuits, the noise models we consider are this EM3 noise model. So this involves making direct XX, YY, or ZZ measurements. And then 2-qubit depolarizing noise correlated with the measurement error occurs associated with each measurement. And this is inspired by Majorana qubits and was used in reference 1. We also consider this SD6 noise model, which is a standard circuit-level depolarizing noise model, which is more commonly used, where you instead use an ancilla and C-naughts for each edge measurement. So how do these, here we're looking at the embedded distance, we're looking at how many logical qubits you can encode using hyperbolic or semi-hyperbolic or hyperbolic or semi-hyperbolic Floquet codes up to at least distance 6. So this is for the embedded distance I mentioned earlier, which is essentially the same as the EM3 distance. So this is looking at the distance in this pair measurement noise model, the Majorana-inspired noise model. And so we can see that for a given number of physical qubits, what this graph is showing is how many logical qubits of at least distance 6 can you achieve with either many copies of these plain honeycomb codes or toric or semi-hyperbolic codes. And so we can see that even with, say, 300 physical qubits, you can achieve you can encode 6 times more logical qubits using hyperbolic Floquet codes. Using 600 physical qubits, you can encode 10 to 15 times more logical qubits. And then with 1,400, you can encode 27 times more. So you get roughly an order of magnitude more logical qubits for a given physical system size. And in 2 slides' time, I'll show some simulations of this code here. So as a small example, here's the Bolster code with encoding 4 logical operators. And this does only have distance 2. But does still achieve some error suppression, and we can see that the logical error rate 4 copies of planar honeycomb codes and the balsa code are essentially equivalent. So essentially using 96 qubits and 4 copies of planar honeycomb codes is completely equivalent to using 16 qubits in this, the balsa code. This is the example I kind of circled in the previous plot. So encoding 32 logical qubits, this is for a 4-10-10 tiling. And so for 600 physical qubits in distance 6, we can see that the logical error rate performance for the hyperbolic code with 600 physical qubits is essentially almost the same as using 6,912 qubits using toric honeycomb codes. Sorry, planar honeycomb codes. So essentially an order of magnitude saving. And then as a larger example, so now this is looking at kind of much larger system sizes. We can see that for an EM3 noise model, actually I haven't put the plot in this slide, I'll just summarizing it. We can achieve a 48 times saving using 48 times fewer physical qubits than honeycomb codes with 21,000 physical qubits. And extrapolating down to low logical error rates, and we show that we can achieve, we only require 32 physical qubits per logical qubit to achieve very low, sort of 10 to the minus 12 logical error rates with distance 12. And then for SD6, we can use 30 times fewer physical qubits in the honeycomb code and achieve a 5.6 times saving compared to surface codes. So the important takeaway from this slide, where I'm just summarizing the results rather than showing all the plots, is that for the EM3 noise model where you have pair measurements, it's already known that the Floquet code performs much better than the surface code. So we already have a 48 times improvement over the Floquet codes, and they themselves already perform better than surface codes in this pair measurement noise model, where you have direct 2-qubit Pauli measurements. For the SD6 noise model, the standard circuit level depolarizing noise model, it flips around, and the Floquet code in this noise model performs a lot worse than the surface code. And so although we outperform the Floquet code by over an order of magnitude, the improvement compared to the surface code in the standard depolarizing noise model is only a factor of 5.6. So it's still a significant improvement, but it's definitely much more promising using the EM3 noise model. So how would you actually implement these codes in hardware? So there are 2 different potential architectures we propose. One is this sort of bilayer architecture on the left, and this sort of diagram is one way to perhaps visualize this. And that's each of these, the topology of these, each hyperbolic surface is kind of fully defined by its genus. And so you can use a non-distance preserving deformation to deform these codes into this sort of bilayer architecture, which has, with the number of holes equal to the genus of the surface, with edges only with edges on the surface of this. This is one way to visualize it, but actually another way to understand why this is a bilayer architecture, or more precisely biplanar, is that the degree of connectivity of this graph is 3. And there's a result in graph theory which shows that therefore at any degree 3 connectivity graph is biplanar. So it can be implemented with 2 separate layers of connections between fixed qubit locations where these the connections in each layer do not cross. But the connections might be long range. Additionally, if you locally in the code, the connections can be embedded into kind of a Euclidean surface with geometrically local operations. And so you could also imagine using many small Euclidean patches, especially with the semi-hyperbolic codes, where locally they are exactly honeycomb codes, and then use long-range links between these modules. These are how we propose you could implement, for example, 2 potential ways you could implement these long-range interactions. So how does this compare to other recent work on LWC codes, one of which we've had a talk on this week? Practical implementations of, there are these 2 references here, of recent work on practical implementations of hypergraph and lifted product codes. And these perform better for the standard sort of the SD6 or similar circuit level noise model I mentioned earlier. But hyperbolic Floquet codes perform a lot better for pair measurements. So when you have 2-qubit, direct 2-qubit measurements. And so in this noise model, we get sort of 1 or 2 orders of magnitude improvements over honeycomb codes and surface codes, which are the state of the art for those noise models. Additionally, the advantage of hyperbolic Floquet codes is that they have this degree 3 connectivity compared to, say, degree 6 or higher in these other works. They're biplanar and modular in the sense I just described, and they're amenable to efficient matching or union-find decoders. Whereas more complicated LTPC codes, there's still a lot of work to be done to have very practical and efficient decoders. And also, there's no issue of sort of having an error flaw in the decoder. And I'll also point out this very nice recent work, reference 3, which also constructs hyperbolic Floquet codes and uses different noise models and has some new examples. So I encourage you to look at that work as well. So in conclusion, we constructed Floquet codes from hyperbolic and semi-hyperbolic tilings. And for pair measurement architectures, we showed that there's almost a 50 times improvement for honeycomb codes and surface codes. And we can require only 32 physical qubits per logical qubit to achieve sort of algorithmically relevant logical error rates. We also demonstrated some small examples with as few as 16 qubits that are experimentally feasible. And all of our constructions are implementable in biplanar or modular architectures and are efficient to decode. And yeah, I'm happy to take any questions.
All right, so forgive my cave dweller's idea of hyperbolic tilings. But the way I always think about them is that you start with the Euclidean tiling and then make one of the shapes bigger, right? So 410 can be derived from 488 just by replacing one of the octagons with a decagon, right? So then, is there a 668 tiling that would be hyperbolic that you could have used? And if not, why not?
We could have used 668 tilings, yes, but we didn't exhaustively search all. There are infinitely many tilings we could have used, and perhaps there could have been some nice examples there. One thing to point out is that the semi-hyperbolic tilings do end up the semi-hyperbolic tilings do have when you're fine graining, you're essentially inserting hexagons. So the 888 tiling, which is fine grained, is very similar to say a 668 tiling. So. Many of the examples we looked at are very similar to that choice of tiling, but yeah, we didn't explicitly construct 668 tilings.
Hi, over the back here. So when you are looking at using the 2-qubit measurements on your Floquet codes and comparing that to the surface code and saying that you're doing much better with the Floquet code, are you also exploiting these 2-qubit measurements when you're measuring the surface code syndromes, or are you doing some other? Is that question making sense?
Yeah, so what I meant by that was in an architecture where your native gate set is pair measurements, alternative compilations of the surface code to pair measurements.
Okay, so you do use the pair measurements on the surface code as well?
Yeah, so this is just considering that specific gate set and noise model and saying the Floquet code is already known, and this is not in our work, in prior work, to perform better than alternative compilations of the surface code to pair measurements.
Okay, thank you.
On a similar note, if I have an architecture that doesn't have pair measurements, is there any value in sort of concatenating this with some kind of lattice surgery-based supporting code that has logical pair measurements as a native gate set? Does that actually get you the benefits of having pair measurements, or is there some sort of reason not to do that?
I haven't thought too much about that. That would definitely be interesting to think about at the very least. Yeah, you could definitely do that. Yeah.
Thank you for the talk. So in your biplanar embedding, could you go back to the slide with the 2 architectures? I think it's relevant to consider how much the cost of the non-locality is in the biplanar embedding. Have you looked at quantifying that non-locality cost in the embedding?
Sorry, I couldn't quite catch that.
Have you looked at quantifying the non-locality cost when you're performing the biplanar embedding?
We haven't quantified that, no. Yeah, so there'll be, in general, very long-range interactions, yeah. But we haven't looked at sort of constructing a specific biplanar layout.
Okay, thank you.
Can you comment on the prospect of doing non-Clifford logical operations in these types of codes?
Yeah, sure. So I think, I guess the way we consider using this is as a quantum memory where you would sort of teleport information into and out. And so there is previous work. I think the reference I cited from on semi-hyperbolic codes, for example, using sort of den twists and lattice surgery to teleport information into and out of the code. So it would definitely be interesting to look at how to adapt that to Floquet codes, and also the talk we saw, I think, yesterday by Thomas.
But any like prospects for like native non-Clifford logical operations, or is that kind of too much to ask? Possibly
yeah,
with
I'm
like
not
higher weights. Okay. Okay.
Yeah, I'm not sure. Yeah, I'm not sure the answer to that question.
Just a reminder that tomorrow, to spice things up a bit, we're going to move to a different venue. So we're not going to be here tomorrow. We are going to be where we had the banquet last night, the Jones Bay Wharf. So if you weren't at the banquet, it's just